Civil Environmental Engineering Senior Design Day 2. We have two classes presented this morning. First is the International Senior Design, or iDesign group. They traveled to Panama in August and then dispersed to some rural low-income communities, and they'll tell you about their work there. That group was advised by Professor Mike Greer and myself. And then second, we have a class that did some projects for Kiewit construction. They'll be talking around 10 o'clock. Maybe we'll try to move it up a little bit in the schedule, but we'll have 4 talks by the iDesign groups and then 4 talks by the Kiewit construction groups. So first, I'd like to introduce Yucca Engineering. They worked on a water distribution system design for a small community in western Panama.
Good morning, and welcome to our final presentation on the Quebrada Arena water distribution system. My name is Victoria Leveille. This is Zgnilec, Jack Ammerman, and Jennifer Robinson. Today, our presentation will consist of our truth assessment, our proposed final design, our cost estimate, and finally our conclusions. In August of 2013, students from Michigan Tech's Senior International Design Program traveled to rural communities in Panama, and our group of 4 members formed Yucca Engineering, like Dr. Watson said. And our goal while we were in these communities was to assess the current water situation. And after spending several days in the community and evaluating the current conditions, Yucca Engineering decided to design a gravity-fed water distribution system so that the community members could get water closer to their homes, and this water is also of higher quality. This is Yucca Engineering's mission statement that emphasizes designing practical solutions.
Throughout the entire scope of the project, we strove to keep these 4 main objectives in mind. The first is to make sure that each member of the community got the recommended 30 gallons of water per day. We wanted to make sure that this water was potable, and likewise, we wanted the entire project to be low maintenance to ensure the longevity of the project, and of course, cost effective. So to begin this entire trip, we traveled from the United States to Panama City and hopped on an 8-hour bus ride all the way over to western Panama to the Leveille market. And we got to a city called San Felix, and we hopped off the bus and hopped into a Chiva, which is basically a souped-up Toyota pickup truck, and started traveling up into the mountains. After a while, the roads got so rough, the Chiva couldn't go any further, so we got off the Chiva and started walking and grabbed our packs, and half hour later, we arrived at the Quebrada Arena community in Cerro Piedra. The region here is incredibly mountainous. It's rainforest jungle, and we spent the majority of our time right here in this valley. Cerro Piedra is translated roughly as Rock Hill.
So the Quebrada community is where we ended up going in Cerro Piedra, and that's where we stayed for 1 week in the village. This community is made up of about 30 houses, and they have a total of 240 people roughly, and that's about 8 people per house we estimate live in each home. Education in the community is present currently. There's a 1-room schoolhouse. They school kids up to the age of 6 or 7. Following those ages, kids go to a nearby community for in a higher up school. For the population in the community, it was interesting. Most of them are under the age of 15 or over the age of 50. And this gap in the middle age for the adults is due to a lack of economic opportunity in the community. So a lot of adults have to leave and go to western Panama, where they work on large farms, or they often go to Panama City or areas around there for work as well. For people that stay in the community, subsistence farming is often their route taken for food income. They grow yucca, which is a root. That's where our team name came from. They also grow coffee and banana as well as rice. As well as a lot of livestock, such as cows, pigs, chickens. This is a typical home in the community. Most of them had metal roofs, as the one shown in the picture, as well as thatched walls, often made of palm leaves. A lot of the homes had dirt floors, but they kept them very clean, even though they were dirt. Cooking in the community is typically done in shelters separate from the main households. A lot of them had metal roofs, just like the homes, and they had open walls. You can see the stones on the bottom of the picture here. That's where a lot of the cooking was done for boiling water. An interesting thing we encountered in the community is the boiling of the water was not done at all for a sanitation reason or for disinfection, but just simply for cooking their food. When they would cook their coffee, they would boil a couple inches of water, and that would form some form of treatment, but then they would add untreated water to that to dilute it. So this cooking of the boiling water, it was important that they were doing that, but it wasn't for the purpose of treating the water, which we found to be an issue.
Currently, water for households as cooking and drinking water is carried by bucket from each water source. Each water source is also used for laundry and for bathing. The task of going and getting water and bringing it back is very, very time consuming, and while speaking with the community members and the Peace Corps volunteer, it was determined that the need for accessible, clean water was of great importance to the community. Yucca Engineering went about assessing the current water situation by first mapping out the community and the proposed water source, as you can see here. The proposed water source is a spring near the top of the community, and this spring is available all year round. Yucca Engineering then tasked themselves with conducting a water quality assessment, and they also did a water quantity assessment at the source. First, Yucca Engineering hiked around the entire community with volunteers, and by using a GPS, we were able to pinpoint, as seen here with the yellow pins, each household in the community. As you can see, the community is not very widespread. It basically goes from uphill to downhill, and that was a good part of our assessment trip, is to figure out where everything was. The source location was also recorded, and a flow measurement at the source was also taken using a volume to time measurement. Another measurement taken was microbial assessments at the source, and 3M feature films were used to do this assessment. These feature films showed positive for E. coli and total bacteria, which indicate that bacterial contamination is in this water, and this can be very, very detrimental to people's health because this can cause severe diarrhea.
The largest part of our data analysis was the actual survey. We tracked quite a lot over the entire community. The community members had the proposed route in mind, and they led us throughout the jungle where they wanted this pipeline to go. As Jenny mentioned, we used a tape rod and GPS. And as I mentioned before, they knew exactly where they wanted to go. Looking at this map here, from house to house, it was pretty straight and incredibly light. When I was incredibly disoriented the entire time we were there. We'd get in a house and they'd say which way back to camp, and I had no idea. But they knew exactly where they were going. There's a little over 300 survey points, and there's just over 3 miles of pipeline here. So the important part about this data analysis of the surveying elevations is this is the mainline elevation profile. Looking at the source, which is the highest elevation within the system, down to the lowest house in the system, there's obviously an elevation difference, and so we knew that a gravity-fed water distribution system would be achievable. The next data analysis was looking at water flow. We wanted to make sure that there's enough water flow within the system to supply the pipeline. So at the source that the community members identified, there was 60 gallons per minute of water during the wet season. However, we were told by our Peace Corps volunteer Jacob Midkiff that during the dry season this may be as low as 1 gallon per minute. So another Peace Corps volunteer, Christopher Kingsley, gave us some water use demands from a community that he had spent time with, which was culturally similar to the one that he stayed with. And through that, we were able to look at demand ratios, which we then applied to the 30 gallons per day per person that is recommended by the Panamanian Health Administration. Through these demand ratios, we were able to achieve a water use pattern to look at local demands of water use for each individual household. And what we determined was that the entire community peak demand was 13 gallons per minute during your typical use hours of in the morning and afternoon. So during the wet season, when we have 60 gallons per minute of availability, there's more than enough water to supply the system. So the water distribution system at this point would definitely be achievable. The next step, following our data analysis, we flew back to the United States and began to design the system. We used a computer model called EPANet, which was incredibly interesting to work with. It taught us a lot. This is a map of the system within EPANet. Just looking at it, so in the upper right-hand corner we have the source, and it flows from there into an inline chlorinator, and then the storage tank. From there, it travels to the rest of the system, branches out to all the houses, and at each house is a tap stand with a faucet. With this system, we're using SDR 26 PVC pipe, chosen for its relatively cheap cost and structural rating capability. And also, you can see there's 2-inch, 1-inch, and 1/2-inch pipe leading up to each individual water service line.
We've designed to have a spring box sitting at the source, and the main purpose of having a spring box is to remove any large solids before they would enter into the system, and to also capture and contain all of that water inside the box. And this is just a general illustration of what a typical storage or spring box would look like. But the water would enter through here, and then there's a gravel layer where any large solids would be removed, and then it would flow into the box and sit there until it flows out of the outlet pipe. And the outlet pipe is 1 inch in diameter, and flowing out of that pipe into the rest of the system is 38 liters per minute. And we've also designed to have an overflow pipe and an access door at the top in case there are any maintenance-related issues or any other reason that somebody would need to get into the spring box. We've also designed, like Jack was saying, 32 tap stands, and those are at each individual household. And we did this because the community members expressed their desires to have tap stands at their homes because they had to walk so far on foot with buckets to retrieve their water. So this will allow them to get water much, much closer to their homes. And this is our design here. We've designed a concrete column, and the splash pad there will reduce the erosion when the water is turned on. And there will be faucets, so the water won't be running continuously. That pipe there is a 1/2-inch PVC, and we're also recommending to have 1 piece of rebar inside that concrete column to increase the structure stability.
To address the need for water treatment, a chlorinator was designed for the system. As Victoria said earlier, primary treatment of the water goes through a gravel filter just before the spring box. Secondly, most importantly, the pathogens are disinfected by chlorine in the inline chlorinator. The chlorinator is made entirely of PVC. The body of it is a 4-inch diameter PVC tube. Inside of the tube sits a capsule, and inside of the capsule sits a 3-inch diameter calcium hydrochloride tablet. These tablets are available locally in Zgnilec and are provided by the Ministry of Health in Panama at no cost. Each tablet is expected to last 1 week within the chlorinator, and after that, it will need to be replaced by a volunteer. The chlorine goes through the chlorinator. As water passes and is contacted with the chlorine, the water is dosed with 1/2 milligram per liter of water. And coupled with the treatment time in the storage tank, this concentration is adequate to treat most pathogens.
So following the chlorinator, and once the water is captured in the spring box, will be a storage tank in our system, which will serve 2 main purposes for the system. The first being, it will act as a way to store water during the night when water isn't being used. And that way during the day there'll be adequate water for the community without having to need a very large inflow into the tank. Also, the storage tank will provide a place for the water to be treated with the contact time with the chlorine. That'll allow proper time for aeration and mixing, and all the pathogens, as much as possible, will be treated in the storage tank before any consumption occurs. We've designed the storage tank to be constructed with concrete blocks and then sealed in with concrete on the side with a sealer. It'll hold 8 cubic meters of water at its peak, and there will be an inflow and outflow pipe as well as an overflow pipe that is designed to run underground to a nearby ravine, which will reduce any erosion around the tank from overflow. In addition to the design components that we've already touched on, we encountered 2 main challenges in designing our system. The first being high pressures due to a lot of elevation changes in the system, and the other being gully crossings that our pipeline has to cross to get to all the homes in the community. So we went about tackling both of these challenges in unique ways, and Jack is going to talk to you about the high pressures.
This is the mainline elevation profile that we showed you before. As I mentioned, the source is in the top left at the highest elevation, going down to the lowest household on the system. The overall elevation difference here is about 900 feet, so you guys know that's quite a bit of pressure buildup throughout the system. The pipe can only withstand 112 psi, and likewise the faucets, we only want them to withstand 80 psi due to safety reasons. So to combat this challenge, we implemented brake pressure tanks throughout the system. Brake pressure tanks, this is just a standard one, are basically small, maybe a cubic meter tank where water flows in. It's reduced to atmospheric pressure and then it flows out again. Flow valve to block overflow during static hours. In order to model this within EPA net, we split up the entire model into 7 subsystems. Where each subsystem begins, a brake pressure tank will be located. And so overall, there's 6 tanks within the system.
For the gully crossings, we chose to design two suspension bridges for the system. Suspension bridges were chosen because they're low maintenance, they're easy to construct, and they're fairly reasonable as far as costs go. For these 2 bridges, we've designed 1/8-inch steel cables to provide stability for the pipes crossing, and they'll be anchored with 1 cubic meter blocks on each end of the pipeline. To protect the main line, which is a 1-inch SDR26 PVC pipe that'll be crossing in the gully crossing, we are recommending a 2-inch PVC pipe encase that pipe, and that way UV radiation won't deteriorate the pipe, and being exposed won't be damaged from foot traffic or from animals crossing.
Alternative water treatment methods were considered to provide the community with adequate clean water to drink. The first being just point-of-use treatment, which is available now in the community. This treatment could be considered as boiling water, dropping chlorine tablets into water, chlorine drops into water, iodine drops in water, as you see an iodine bottle there. This would give the community members freedom to choose what type of method they wanted to clean their water with, though currently this is not employed in the community. The inline water treatment method was favored, and an option for this would be a inline photocatalytic reactor, where a photocatalyst, such as titanium dioxide, is put just like the chlorinator. It's just put in line, and it's exposed to sunlight, and enhances UV treatment. The cost and maintenance of a system like this did not compare to the low maintenance and low cost of the chlorinator.
With our final design complete, we could determine and quantify the materials that we needed for the actual design. And as you can see here, our final cost estimate is $12,300, with our most expensive item being the pipeline at just over $5,000. And this is because of the amount of PVC pipe that we needed to service the system. And with the total cost, we were hoping that it would come in around $10,000. And obviously this is a little bit higher. So it's important to note that we did add a 10% contingency fee. And that's just because we're not sure what could happen in any unforeseen circumstances. And we also have not included labor. We're hoping that the community can provide those needs.
So as Victoria just stated, we are hoping the community will be able to offer 5 labor crew hands to work with 1 Peace Corps volunteer in the construction process of the design. And with this crew, we've estimated that complete construction will last a total of 6 months, which unfortunately spans the duration greater than the dry seasons when construction will happen. So we're suggesting that construction be broken down into 2 main sections, 1 each dry season. And for the first dry season, the tank, tap stands, and storage tank should be designed and constructed. And those can be built first because they're made of concrete, they're very structurally sound, and being exposed to the elements for 1 extra year shouldn't damage them at all. Come the second dry season, we are suggesting the pipeline be laid, and as that is being laid, that the pressure brake tanks be placed as well as the gully crossings. The pressure brake tanks and the gully crossings will have to be put in as the pipe gets laid, because the exact location of the pipeline right now can be estimated but not exactly determined, because any rocks or large trees that weren't accounted for in the survey, they might interrupt the pipeline.
So Yucca Engineering has designed a proposed gravity-fed water distribution system that will allow the community members to retrieve water much closer to their homes and of a higher water quality standard. We're going to submit this design to the Peace Corps, and we're hoping for funding so that the design can become a reality and the community members can actually
You show a 0.5 parts per million, is that your residual on your chlorine, or is that your?
That's just the dissolution rate of the tablet.
What's your
so-
C, what's your CT?
The C part is 0.5 parts per million. The T is 2.7 hours in the storage tank, equating to 28 milligrams minutes per
I
liter.
think you're a little low on that. One low.
Okay, thank you. Yes, sir.
Question about your cost estimate. It looked like the tap scans turned out to be a fairly high cost item. 32 cap scans, $1,500. Did you do any value engineering? I mean, are there other alternatives to that concrete?
Yeah, there are.
That might be less expensive.
There's a few other alternatives, such as they'll run just a wooden post that might be buried a few feet, and that'll support the pipeline coming up, as well as just putting it against a tree. But the reasons we avoided those options is because we're trying to protect the pipeline as much as possible, and any place that's exposed is going to increase the odds of it being broken. So if this cost is too high for the project to happen, that's definitely one method that could be taken to reduce the cost. Yeah.
And speaking of breaking, are there intermediate valves, isolation valves along the pipeline if you had a break or something, since it's all gravity fed?
So isolation valves definitely would be an option to throw in there. The Peace Corps volunteer that is currently with the community expressed interest in putting them in, and we have looked at putting them in after each individual component, isolating each branch. So they're definitely figured into the overall cost estimate of the pipeline.
There'll be some valves in the brake tanks, right?
Yeah, absolutely.
Any other questions?
You need to say a little bit about that chlorinator. Did you design that chlorinator? Is that some standard design?
This is a standard design. The Ministry of Health of Panama suggests this type of chlorinator, and in the past, Peace Corps student, Mr. Lerner, has put in a system with this chlorinator in there. And that's where we got the empirical data for how fast the chlorine tablets dissolve. And he was actually inside a very close community, and he was validating the effectiveness of the chlorine.
Any other questions in this group?